The elements in group 18 are helium, neon, argon, krypton, xenon, and radon. These elements are collectively referred to as noble gases. The term noble gases implies that these elements tend to be chemically inert or unreactive, just as noble metals that show reluctance to react under normal conditions. However, compounds of xenon, such as fluorides, oxides and oxyfluorides, and fluorides of krypton are known. These compounds can be prepared only under drastic conditions at high pressure and temperature. Now let's look at the electronic configuration of the group 18 elements. The general valence shell electronic configuration of these elements is Ns2-Np6, except for helium. Note that the electronic configuration of helium is 1s2. Although helium does not possess an octet, it resembles other elements of the 18th group. The electronic configuration of these elements are listed in the table here. You can see from the table that the Np subshell is completely filled in all the elements. Due to the duplet or octet configuration in their valence shells, the elements of this group are highly stable. In other words, as these elements have closed shell structures, they have less or no tendency to form compounds. As these elements do not have a tendency to lose, gain, or share electrons with atoms of other elements, their valency is 0. The stability or inert nature of these elements is further attributed to the symmetrical arrangement of their electrons. Let's now discuss the occurrence of these elements. Owing to their inert nature, all the noble gases occur in free state. All the noble gases, helium, neon, argon, krypton and xenon, except radon, occur in the atmosphere. Note the percentage abundance of these elements listed here in the table. These gases make up approximately 1% by volume of the atmosphere, in which argon alone constitutes 0.93%. As argon is quite abundant in air, it can be obtained from liquid air by fractional distillation. On the contrary, since helium is scanty in the atmosphere, its recovery from air would become highly expensive. Natural gas deposits are the most important commercial and economical source of helium. Helium is also found in the minerals of radioactive elements, uranium and thorium, such as clevite, monazite and pitchblende. These minerals give off helium gas on being chemically treated. Certain water springs contain helium, neon, and argon in the form of dissolved gases. Radon is a radioactive substance that is produced by the decay of radium and thorium minerals. Let us now discuss the trends in some of the atomic properties of the group 18 elements. The table here lists the trends in some of the atomic properties of the group 18 elements. The atomic radii increase on descending the group with an increase in the atomic number. This is because of the addition of a new shell at each successive element on descending the group. Talking again about their electronic configuration, you know that these elements have closed shell structures, which render them stable. As a consequence, these elements have very high ionization potentials. In other words, the removal of electrons from the valence shell is very difficult. However, you can see from the table that ionization enthalpies decrease gradually on descending the group with an increase in the atomic size. Note that the ionization enthalpy of a noble gas is the highest among the elements of the same period. Again, because the elements of group 18 have stable electronic configurations, they do not have a tendency to accept electrons. Hence, they have very high positive values of electron gain enthalpy. Let us begin our study with the physical properties. You know that the elements of group 18 have closed shell structures, because of which they have no tendency to form compounds under normal conditions. Owing to their inert nature, these elements exist in free state as monoatomic gases. These elements are colorless, tasteless, and odorless gases. They are sparingly soluble in water. The forces holding the atoms together are weak van der Waals forces of attraction, which is evident from the very low values of enthalpy of vaporization as shown here in the table. The weak van der Waals forces of attraction are also called London dispersion forces. The magnitude of van der Waals forces increases on moving down the group with an increase in the polarizability of the atoms. You can see from the table that the melting and boiling points of these elements are very low. This is, in fact, due to the weak van der Waals forces of attraction or weak dispersion forces. However, the melting and boiling points increase on descending the group with an increase in the magnitude of the van der Waals forces of attraction. In other words, more energy is required to overcome the forces between the atoms with an increase in the atomic size or with an increase in the diffusion of the electron cloud. Further, due to the weak van der Waals forces, noble gases can be liquefied at very low temperatures. With an increase in the magnitude of the van der Waals forces down the group, the ease of liquefaction of noble gases also increases. Note that helium has the lowest boiling point among all the elements in group 18. Moreover, it has the lowest boiling point of any element, just 4.2 Kelvin. Liquid helium finds use in cryoscopy to obtain the very low temperatures required for superconductivity. Helium has the unusual property of being able to diffuse through glass, rubber, and plastic, which are commonly used as laboratory materials. Let us now discuss the chemical properties of these elements. You know that the inertness of these elements to chemical reactivity is attributed to their stable electronic configuration, high ionization enthalpy, and higher positive electron gain enthalpy. Before 1962, several attempts made by chemists to force these elements to react and form compounds were unsuccessful. In 1962, Neil Bartlett predicted that xenon should react with platinum hexafluoride just as dioxygen because the first ionization energies of both oxygen and xenon are nearly the same. His efforts were successful. He was the first to prepare a compound of xenon called xenon hexafluoridoplatinate 5. Later, many compounds of xenon were synthesized, including fluorides, oxides, and oxyfluorides. The data in the table for ionization enthalpy here shows that the chemical activity of group 18 elements increases with the decrease in the ionization enthalpy on descending the group. The ionization enthalpies of helium, neon, and argon are too high for them to form compounds. On the other hand, krypton forms only krypton difluoride, since its ionization enthalpy is slightly higher than that of xenon. Even though radon has less ionization enthalpy than xenon, it forms only some compounds like radon difluoride and some complexes. Since radon has no stable isotopes. However, xenon forms a markedly greater number of compounds. You know that in 1962, Neil Bartlett predicted that xenon should react with platinum hexafluoride just as dioxygen, because the first ionization energies of both oxygen and xenon are nearly the same. His efforts were successful. He was the first to prepare a compound of xenon called xenon hexafluoridoplatinate 5. Later, many compounds of xenon were synthesized, including fluorides, oxides, and oxyfluorides. Let us first discuss the methods to prepare xenon-fluorine compounds. Xenon directly reacts with fluorine to form a binary fluoride, which may be xenon difluoride, xenon tetrafluoride or xenon hexafluoride. The product depends on the ratio in which xenon and fluorine react. When a mixture of xenon and fluorine in the ratio of 2:1 is heated at 673 Kelvin in a sealed nickel vessel at 1 bar pressure, xenon difluoride is formed. Xenon tetrafluoride is obtained when a mixture of xenon and fluorine in the ratio 1:5 is heated at 873 Kelvin in a sealed nickel vessel at 7 bar pressure. Xenon hexafluoride is obtained when a mixture of xenon and fluorine in the ratio 1:20 is heated at 573 Kelvin in a sealed nickel vessel at 60 to 70 bar pressure. Xenon hexafluoride can also be obtained by the reaction of xenon tetrafluoride and dioxygen difluoride at 143 Kelvin. Let us now take a quick look at the structural aspects of the fluorides of xenon. The central atom, xenon, in xenon difluoride undergoes sp3 dehybridization. Xenon difluoride has 5 electron pairs. Of these, 3 are lone pairs and 2 are bond pairs. The structure of xenon difluoride is linear owing to the presence of the 3 lone pairs of electrons on the central xenon atom, as shown here. The central atom, xenon, in xenon tetrafluoride undergoes sp3 d2 hybridization. Xenon tetrafluoride has 6 electron pairs. Of these, 4 are bond pairs and 2 are lone pairs. The structure of xenon tetrafluoride is square planar owing to the presence of the 2 lone pairs of electrons on the central xenon atom, as shown here. The central atom, xenon, in xenon hexafluoride undergoes sp3 d3 hybridization. Xenon hexafluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. The structure of xenon hexafluoride is distorted octahedral owing to the presence of the single lone pair of electrons on the central xenon atom, as shown here. Finally, let us study the properties of xenon fluorides. All the fluorides of xenon are white crystalline solids. They are sublimable at room temperature. They are strong oxidizing and fluorinating agents. For example, xenon difluoride oxidizes chloride ions to chlorine, while xenon tetrafluoride oxidizes iodide ions to iodine, as shown here. Similarly, xenon tetrafluoride fluorinates platinum and sulfur tetrafluoride, as shown by these chemical equations. Xenon tetrafluoride and xenon hexafluoride react violently with water, while xenon difluoride reacts slowly with water. You can see from the equations that the products of the slow hydrolysis of xenon difluoride are xenon, hydrofluoric acid, and dioxygen, while xenon tetrafluoride and xenon hexafluoride undergo hydrolysis to give xenon trioxide as the main product. Xenon fluorides form complexes called xenon fluoride complexes. They form complexes with covalent pentafluorides, such as phosphorus pentafluoride, antimony pentafluoride, and arsenic pentafluoride. Note that xenon fluorides act as fluoride donors. Xenon difluoride reacts with phosphorus pentafluoride, while xenon tetrafluoride reacts with antimony pentafluoride to form cationic species, as shown here by the chemical equations. On the other hand, xenon hexafluoride can also act as a fluoride acceptor with rubidium fluoride. Let us first discuss the methods to prepare xenon oxides and xenon oxyfluorides. Xenon tetrafluoride and xenon hexafluoride undergo complete hydrolysis to give xenon trioxide, as shown in these chemical equations. On the other hand, xenon hexafluoride undergoes partial hydrolysis to give oxyfluorides such as xenon oxytetrafluoride or xenon dioxydifluoride, as shown in the equations here. Try to answer this question on your own before looking at the answer. Is the hydrolysis of xenon hexafluoride a redox reaction? No. As there is no change in the oxidation state of any element in the reactants and products, the hydrolysis of xenon hexafluoride is not a redox reaction. Let us now take a quick look at the structural aspects of some of the oxides and oxyfluorides of xenon. The central atom, xenon, in xenon trioxide undergoes sp3 hybridization. Xenon trioxide has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. Note that there are 3 d-pi-p-pi bonds in the molecule. The structure of xenon trioxide is pyramidal, owing to the presence of a lone pair of electrons on the central xenon atom, as shown here. The central atom in xenon oxytetrafluoride undergoes sp3d2 hybridization. Xenon oxytetrafluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. Note that there is 1 d-pi-p-pi bond in the molecule. The structure of xenon oxytetrafluoride is square pyramidal owing to the presence of a lone pair of electrons on the central xenon atom, as shown here. The central atom in xenon dioxydifluoride undergoes sp3d hybridization. Xenon dioxydifluoride has 7 electron pairs. Of these, 6 are bond pairs and 1 is a lone pair. Note that there are 2 d-pi-p-pi bonds in the molecule. The structure of xenon dioxydifluoride is seesaw owing to the presence of a lone pair of electrons on the central xenon atom, as shown here. Finally, let us study the physical properties of xenon trioxide and xenon oxytetrafluoride. Xenon trioxide is a colorless, explosive and hygroscopic crystalline solid, while xenon oxytetrafluoride is a colorless liquid. Let us begin our study with the uses of helium. Helium is not inflammable and has a very low density. That is why it is used to fill weather balloons and airships. Note that it is less dense than air. 1 cubic meter of helium gas can lift 1 kg. You know that helium has the lowest boiling point among all the elements in group 18. Moreover, it has the lowest boiling point of any element, just 4.2 Kelvin. Hence, liquid helium is used as a cryogenic agent to perform experiments at very low temperatures. Liquid helium finds use in cryoscopy to obtain the very low temperatures required for superconductivity. Liquid helium is used to cool the superconducting magnets used in nuclear magnetic resonance spectrometers. Liquid helium is also used in the medical field to cool the superconducting magnets that are essential components of magnetic resonance imaging (MRI) systems. You know that MRI systems are used for clinical diagnosis. It is used as the cooling gas in gas-cooled nuclear reactors and as a flow gas in gas-liquid chromatography. Helium is used to dilute dioxygen in the cylinders carried by sea divers. This is because it is only slightly soluble in blood even at the high pressures that divers encounter deep in the sea. Let us now discuss the uses of neon, argon, krypton and xenon. Neon is used in small amounts in discharge tubes and fluorescent bulbs that give the familiar red-orange glow of neon signs. Hence, these tubes are used extensively in advertisement displays. Neon bulbs are also used in botanical gardens and greenhouses as neon stimulates the growth of plants. Argon is widely used to provide an inert atmosphere in laboratory apparatus and for metallurgical processes, such as in welding stainless steel, aluminium and magnesium. Also, it is used to fill electric light bulbs to prolong the life of the filament. Krypton is used in filament lamps and discharge tubes, while xenon is used in discharge tubes to produce the high-speed flash required for photography. Radon finds use in radiotherapy for the treatment of cancer.